So far, you have seen how to calculate the incident irradiance based on the tilt angle for the standard flat-shaped PV module. In this video, I'm going to talk about some advanced irradiance modeling methods that were developed for custom-made or non-standard PV modules and for complex surrounding environments. In particular, an optical modeling approach, another approach based on a LIDAR, and a combination of both approaches will be discussed here. Further, I have introduced the 4 scenarios that are most likely to be encountered by a PV system engineer. For each of those scenarios, a particular irradiance model will be applied. The first scenario is when you have a standard PV module in a free horizon. The second scenario is when you have a non-standard PV module in a free horizon. The third scenario is when you have a standard PV module in a complex horizon environment. Finally, the fourth scenario is when both custom PV module and complex horizons are involved. So let us start with the first scenario. When only the standard PV module and the free horizon are available, the irradiance calculation can be carried out using the tilt angle method. For this, as you already know, the direct irradiance, diffuse irradiance, and the albedo on the PV module surface are computed separately, and the total irradiance is determined for each interval of time. Then, the best combination of module tilt and azimuth angle is found by calculating an optimum value for the specific location. This is determined by iterating the total energy on the PV module surface for different combination of module tilt and azimuth angles. But one major disadvantage of this method is that it cannot be used on a custom-shaped or non-standard PV modules. This is because such PV modules might have non-homogeneous irradiance distribution on their surface due to their geometrical shape. Hence, it becomes quite difficult to accurately simulate such irradiance distributions using this basic method. Hence, to solve this problem, a new type of irradiance model was developed. In the next scenario, where free horizon and the non-standard PV modules are considered, this flexible irradiance model is discussed. To calculate incidence irradiance on non-standard PV modules, an optical modeling approach is followed. In such an approach, first a ray tracing software is used to perform simulations on a 3D geometry, which in our case is a PV module. Then a separate sky radiance model, such as Perret's model, is simulated. Finally, the output from the sky radiance model and the ray tracing outputs are combined to calculate the incident irradiance on the selected PV module. Let me explain how this model works with an example of a non-standard PV module as shown in this figure. Unlike the more popular flat-shaped PV modules, the module shown here is ondulated. Ondulations are profiles that have continuous wave-like design consisting of peaks and valleys. Due to the ondulations for such a PV module, the irradiance distribution on its surface will be non-homogeneous, as can be observed from the figure. In the optical model, the geometry of the PV module is created and the light rays with a certain intensity are simulated to impinge on the module surface from all angles of incidence. After this ray tracing simulation is complete, a so-called sensitivity map is generated as output. A sensitivity map contains information about a surface sensitivity to incident light at all angles of incidence. It is primarily dependent on the shape of the created geometry. Next, as I mentioned, a sky radiance model is used to create a so-called sky map. The sky map contains information of the location sky radiance distribution for a particular instance in time. The input to the sky map are the easily measurable DHI and the DNI. While the sensitivity map is geometry dependent, the sky map is purely location dependent. Finally, the total irradiance incidence on the surface is calculated by integrating the product of the sensitivity maps and sky maps. For the undulated module shape, the incident irradiance on its surface, calculated for one instance in time, will look like this. In general, this optical model can be used for any geometrical shape. That is, the incidence irradiance on any surface and in any location can be predicted. Let us next move on the third scenario, where a standard PV module along with complex horizons are considered. For this, I'm going to explain to you about an irradiance modeling approach based on the use of LIDAR. The use of such an approach improves upon the existing options available when simulating complex surrounding environments. It combines the advantages of an on-site location survey method and a remote assessment survey. As you know, LIDAR is a surveying method that uses laser light to measure distances. The data is generally collected by air, using planes or helicopters. By using the LIDAR data, 3D information about the shape of the available surfaces for a certain location can be generated. Such information may include buildings, nearby trees, or even faraway mountains. An example is shown in this figure, where LIDAR data for a certain location in the Netherlands were obtained and its 3D information was generated. Here you can see all the objects present in the location, including a few tall buildings that are nearly 100 meters in height. Once the LIDAR image of the intended location is generated, the region where the PV modules will be installed is chosen as the area of our interest. In our case, the facades of one of the tall buildings in the location is chosen as that area. Next, we have to carry out a location survey and accurately determine the obstacles that affect the irradiance reaching this area. As you know, one of the tools used to carry out this task is by using the Hori catcher, which captures the horizon of the selected area and displays the obstacles present in them. However, one of the advantages of using the LIDAR method is that this location survey is done remotely, unlike the Hori catcher approach. The figure shown below is a location survey carried out remotely using the LIDAR data. As you can see, there is a striking similarity between the Hori catcher image and the LIDAR image. Moreover, when the sunpaths are included, it can be observed that both the images show blockage of direct light in the afternoon periods throughout the year. Another feature using the LIDAR approach is that we can quickly determine the horizon at each point in the facade of tall buildings. In this figure, you can notice that change in horizon as height of the building is increased. The optical model is a flexible method to simulate non-standard PV module shapes. The LIDAR approach is an easy way to carry out the location survey of complex horizons. When both methods are combined, a PV system simulation of non-standard shapes in complex horizon environment can be carried out. This is a typical example of an infotainment spot that is made of curved thin crystalline silicon PV modules. For such a PV modules, we know that the optical model is used. Moreover, when an infotainment spot is placed in a complex environment, such as this location in a TU Delft campus, the LIDAR approach is used to survey the landscape. By combining the benefits of the optical model approach and the LIDAR approach, the simulation of such a PV module and its surrounding environment can be carried out. Here, on the left-hand side image, you can see the landscape survey carried out for the TU Delft location. On the right-hand side, the sensitivity map of the curved PV module, superimposed by the LIDAR image, is shown. To recap, in this video you learned about some advanced irradiance modeling techniques. 4 scenarios were discussed when standard PV module and free horizon is considered. The tilt angle approach is used. When a non-standard PV module is used, the optical model approach is followed. On the other hand, for complex environments, a LIDAR approach is applied for standard PV modules, and the combination of LIDAR and optical model approach is applied when non-standard PV modules are used. With this video, we conclude this section about irradiance modeling. In the next week of this course, we will look into the different aspects of PV modules.